here, remember I slammed a few examples on the board?
Right.
I said if you want to take a peek and go for it. So you guys, I'm just copying it back up there. So question. Consider this differential equation and construct a slope field. And in constructing your slope field, I want you to use isoclines to do just that, instead of just drawing all these individual little ticks. And when I say use isoclines to construct the slope field, I mean the following. I want you guys to treat y prime as various different constants and see the corresponding equation you generate in x and y when you slam those constants in for y prime in that differential equation. For example, using a bit of color. If y prime is equal to 0. Sorry, can I redo that, you guys? Can I draw the 0 in red so that when I go to the corresponding Cartesian coordinate system, you see the tick as a very short red line segment? And let's talk about the corresponding isocline. So does everybody agree that if I plug 0 in for y prime in that differential equation, don't I really get this? Let's see how yesterday worked out with my first example. Who cares? What's the significance with what I put on the board in red and in green?
Shows you all the places where the slope is 0.
I think it shows all the places where my solution to DE is going to have a slope of 0. I think for any solution that passes through this green line, the slope of the tangent line is going to be 0. And so let me go ahead and try to portray that in my Cartesian coordinate system. X-axis. Y-axis. Oh, let me put a few ticks in here, you guys. When I take a peek at this green line, y equals 1. If any solution passes through it, the slope of the tangent line is simply going to be 0. Next, if I substitute in for y prime, I don't know, something else like maybe how about a positive 1? Doesn't it tell me that 1 is equal to y minus 1 to the 2/3? Or shall we say y minus 1 is equal to you math dx per 1. I can't hear anything. Plus or minus 1. So I think y is going to be equal to 1 minus 1, or y is going to be equal to 1 plus 1. So I think there's 2 isoclines corresponding to the slope value, a positive 1. Here they are in green. Y equals 0 and y equals 2. Well, here's y equals 0. Here's y equals 2. And I yet again have horizontal ticks, do I not?
Why did you write y equals 0 for y equals 2?
Sorry, that wasn't meant to be a mistake. That was my mistake. What did I say in English?
Y equals 2.
I'm glad I said it.
Yeah.
Just listen to me. Don't look what I write.
And then there's y equals u.
What's that?
0.
That's
oh,
a partial
it's a bad
0.
0. Okay.
It's a special 0.
We're going to get somewhere today. And you guys, horizontal ticks? No. Actually, in red, I think the ticks are going to have a slope of positive 1, meaning that if any solution passed through this horizontal line in green, the slope of the tangent line at those points, or at that point, is going to be positive 1. Same thing with this isocline. Next. Oh, you guys, I'm tired. You know me by now. I make silly arithmetic errors. Do you like a 2? Do you like a 2?
Yeah, sure.
No, I don't. I think we did look like nasty numbers. I want to be clean. I want to have cleanups. I want to beat that clock. I don't want to do a lot of arithmetic. I don't want to do a lot of arithmetic.
Well, negative 1.
Then I won't get any isoclines.
4.
Nice. Because now when I plug 4 for y prime, I take the square root of both sides. I get a 2. I raise each side to the 3rd power. That's going to give me an 8. And so I think my isoclines are going to be actually, what did I say it was? 4? So I think my isoclines get y equals 9 or y equals 9? Plus minus. Well, y equals, you said 9? I got y equals 9 or y equals negative 7. Is that correct? You guys just double check my arithmetic. So y equals 9 or negative 7. I think for those 2 lines, I'll cheat and not unitize carefully anymore. I think for these 2 isoclines, the slope of the tangent line is even steeper than positive 1, it's positive 4.
So how accurate do you actually have to be with those isoclines? Because
Oh, look how fast I am.
I know.
I'm not accurate at all. As a matter of fact, I think you even stop.
Okay.
I don't think I have to do anymore, because I think if I allow y prime to be something as big as 9, steeper slope,
Yeah.
I think the isoclines themselves are going to be separated even further away from the line of y equals 1, just by observation. And so I see the higher my isocline becomes above y equals 1, the steeper the red ticks. Looks to me, I've got curves that kind of look like they're exponential, at least behave in the same fashion. Would you guys agree? And so maybe even with my purple pen, trying to draw in some trajectories, let's give it a shot. What do you think? Maybe here's another one. Maybe here's another one. Sorry for my lousy purple. What about this purple option? Oops.
It doesn't like you.
It doesn't look true. Do you think this is a solution? I asked, do you think that's a solution?
Yes.
I think it is, because the equation of that horizontal purple line is y equals 1. But when I plug in for y on the right-hand side of the equal sign, what do I get? 0. But if y is equal to 1, what's y prime?
0.
I think it truly satisfies the differential equation. By the way, can I introduce some new vocabulary? If ever I have a solution to my DE of the form y equals some constant, I sometimes refer to that as an equilibrium solution. So I think in this example number 2, y equals 1 is a solution, but I will also classify it as equilibrium solution because it's a solution of the form y equals some constant. Do you guys think this might happen in red? No, I mean, sorry, in black. Do you think it's at least remotely possible with what we have so far? No. Why not?
You would have to cross the line of y equals 1.
And you know I can't cross the line y equals 1, right? I'll ask it again. And you know I can't cross the line y equals 1, right?
Yeah.
Do you?
Because it's the partial derivative is continuous.
The partials are
Continuous.
are they?
I mean, discontinuous.
Oh, what does that mean then? Beautiful. I think I can't say anything about the existence of that solution in black. I know I've got one solution, y equals 1. But if you take a peek at applying the existence uniqueness solution, I think it yields no results. After all, look at my function f. Is my function f continuous everywhere? Yeah, it is. It's safe. But if you look at the partial of f with respect to y, isn't the partial of f with respect to y, isn't that just 2/3 times 1 over y minus 1 to the 1/3?
Yeah.
And I think that's discontinuous when x is, well, maybe nothing yet. But when y is equal to 1, and when you look at that solution I drew in purple, that horizontal line y equals 1, every single point on it has a y coordinate positive 1. Therefore, I think the existence uniqueness theorem says nothing about the existence or uniqueness of that solution y equals 1. Could that happen in black with what I know so far? I guess maybe. Because I do think the existence theorem is inconclusive. So in reality, beyond today, what the heck would you and I do to find out if there really is more than one solution passed through that line? Well, maybe you find some way to solve the DE and see what the solutions look like. All I'm suggesting is that with this superficial glimpse geometrically of the solutions, I do think I'm somewhat inconclusive when it comes to that theorem. Are you there? Okay. I'll erase it anyways. It doesn't seem feasible that it happens, but I'll erase it. Does anybody have the rest of the examples I gave you last time in class?
Yeah.
I know.
So what's my next one?
X times y plus 2.
X times y plus 2. Like that? Well, everybody, same idea. When I come in, actually, no, maybe I'll backtrack. Maybe not same idea. Let's do something different. Do you think there's an equilibrium solution? Yeah, I think so. I think it's clear that y equals -2. And so y equals -2 is indeed an equilibrium solution. So if you guys don't mind when I draw my xy coordinate system, I'm going to slam it in real quick. So you guys, can you give me a hand? What do you think you can say about the slope of the ticks in red? So when I plug 2 and 4, what do I get? What do I get for y prime? Yeah, you guys has to be 0. Because I think if y is equal to -2, the entire right-hand side is equal to 0. Y prime is 0. I know what it looks like. It looks like this because the ticks are all obviously horizontal. I'm being silly. I'm saying too much. Next. Let's pick some values of y prime out of thin there. How about something like, how about -2? Let's see what the corresponding isocline is, and I'll be consistent with my color in green. Anybody? So y prime equals 1. You meant y, not y prime, right?
Yeah.
Anybody? This is a Math D question. You remember Math D? Really?
A few steps in my head.
Negative. Oh, it's painful. 2
Over x.
over x minus 2. What does that look like?
Hyperbola.
Looks like hyperbola. Okay, so maybe this example, unlike my first two, I don't get isoclines that are just lines. I get curves instead. Let's draw them in. We know y equals 1 over x looks like. Y equals 2 over x is simply the standard parabola, standard hyperbola stretched away from the x-axis by a factor 2. Now it's reflected through the horizontal x-axis. Now it's translated, 2 units down. Roughly speaking, I think it looks like this. And I'm not being that careful, you guys, but something like this. That'd be the graph of y equals -2 over x minus 2. I hope you guys agree.
Yes.
It's just that. If any solution to that differential equation passes through this one particular hyperbola, then the slope of the tangent line of that solution as it passes through this hyperbola is -2 units. I'll try to draw all these ticks in red so the slope looks like -2. Even though I might be a little bit sloppy, a little bit off. Next. Well, if I sketch in, or how about conjure up a number out of thin air like -1? Then I think that necessarily implies my isocline is y equals -1 over x minus 2. I like it. I think it's the same graph I already have in green on the ink board. It's just not quite as pulled away from the x-axis. I said pulled away from the x-axis, didn't I? In the end, not quite as pulled away from the line y equals -2. And so I think I get a curve or a hyperbola that looks more like this. Oh, but slopes end up being -1. So still a negative slope, just not as steep as with the previous hyperbola. Do you guys agree? I keep asking if you agree, only because I know I'm kind of sloppy on the inquiry. Now plugging 0 for y prime, I get yeah, a waste of time. We've already done it. So I'll skip 0 and come to +1. But doesn't that give me this? It's an isocline. Oh, by the way, I think in green what that looks like is exactly what I already drew in green with my last hyperbola. I'm just going to reflect it through that horizontal line y equals 2. And I think it looks something like this. It's just that any solution to the original DE passed through that isocline is going to have a slope of this time, +1. You guys tell me if I'm moving too fast.
All right, so one of those ticks is way, way off.
What do you mean?
The one on the top that is not even on the line.
Oh, okay. Jeepers. Use your imagination. Oh, can we apply the French technique? Yeah, sorry, sir.
So when y prime is 0, would x equal 0 be an isocline? Or is it just y prime?
No, we're definitely going to go back to that. We will. But let's do this first. The French technique?
That sounds interesting.
What is the French
But all it takes to have steeper slope?
Yeah.
Brad, I'll try to stay on my bicycle.
Okay.
And so do you guys think for all the hyperbolas further and further away from that equilibrium solution, the ticks are just getting more steep in the positive or negative direction? But somebody gave away the key. I was hoping you would have looked at it to the end. You have to confess, if y is equal to -2, y prime is 0, but also if x is equal to 0, y prime is equal to 0. But what does the graph of x equals 0 look like? It's a vertical line that's sitting right on top of the y-axis. And so I think if my solution passed through the vertical y-axis, slopes there as well are going to be 0. Do you guys agree? So to the best of our abilities, let's see if you and I can't sketch a solution pass through one of these points. I'll close my eyes. I'll pick a point out of thin air. How about right here? So if a solution passed through that point, let's talk about what this overall graph's going to look like. Can we move in the leftward direction? As I move left, these are negative slopes. My y-value is getting bigger. But then at a slower and slower rate. Till all of a sudden I hit the y-axis and my tangent line is horizontal. Then as I move further and further to the left, beyond that vertical, axis, I think the slopes are getting more and more positive. And I think even to the right, if I move in the other direction from that initial point, my slopes are getting more and more negative. Something like that. Is that a parabola? I don't know. I wouldn't know that unless I solve the DE in some kind of analytic fashion and find out what that curve really looks like, algebraically speaking. Because you guys understand, parabolas have very specific curvature, correct? A lot of fun clicks. And you understand the reflective quality of a parabola, right? All right. Is there anybody in this room who might be interested in doing honors for this class?
What do you get for honors?
Prestige.
Prestige? What does honors involve?
Sierra College is too small to offer honor courses, and I was one of the faculty members on the honors board when we first formed it. And what we decided we'd do, since we're so small, is we allow professors to allow certain students in certain classes to sign contracts that would earn them honors designation on the transcript.
Okay.
And so if you're interested, I mean, that's something you can check out. I almost always have honors contracts in Math 33.
What do the contracts involve?
You get the path of the B to get the honors, right?
Oh no. I was on the honors committee. I made darn sure that a faculty member can make the requirements more stringent. And so so in my contracts, I do mandate that you have to earn an A at the end of the semester to get the honors specification. It's just extra projects for line of class. The only reason I made me thought of it is, you know what a parabola looks like? Or sorry, I misspoke. You know the quality of a parabola. There's a focal point. It's a line of symmetry.
Yep.
You stand at the focal point. You throw a projectile in the direction of I don't know, anything you darn well please. You hit the parabolic reflector, but then you
Just goes bounces
reflect off in
straight
such a
forward.
way that you're running parallel to central line of symmetry. Same thing in green. Stand at the focal point, throw a projectile here, and run parallel. So if you're interested, anybody's interested in honors, my first question is going to be this. That's a funky looking curve. Central line of symmetry. If this curve has that kind of reflective quality, is it necessarily parabola?
Yeah.
It's a really good question.
Yes.
Ah, but to prove it, you need to build and solve differential equations.
Okay.
Sorry, I'll come back. I'll come back.
So if we're interested, you'll give us the proper question.
Yes. Well, actually, I'll state the question just like that. If some curve has this reflective quality that a parabola has, is it necessarily a parabola? All right, I'll come back. You guys, do you mind if I don't draw any more trajectory? Yes, sir. I'm sorry.
Alright, so our isoplines were hyperbolic, right? And-
Yes, they ended up being hyperbolic in this example.
Okay, I was just confused because I thought we were going to reflect on the other side as well for our particular solution. I thought we ended up with a system of hyperbolas, not necessarily parabolas.
You know what? That's certainly a possibility. And maybe if I somehow analytically solve this differential equation, I found my solutions are hyperbolous as well, then you're right. It's just since I didn't go so far as to solving this particular DE, with what I know so far, I can't determine whether or not there's another branch, whether or not this really is a hyperbola. I just can't answer the question yet. So I confess it's still a game of geometry I'm playing. Is fairly limited in what I can do. You know what? Maybe this example, something nice does happen. Maybe this example, sorry if I didn't think about this. Is it the case that every solution is passing through a point uniquely? In other words, if you guys apply the existence uniqueness theorem, what can you conclude?
Partial derivative is continuous.
The partial of f with respect to y is continuous, and f is continuous clearly for all points x comma y. Therefore, every single point in the Cartesian coordinate system, if a solution passed through it, is going to be unique. Do you guys agree?
Yes.
Okay, you again, yell at me if I'm talking too fast. All right. Who had that list? Does anybody have the next one? If I'm not traveling too fast?
Y times y minus 1.
Oh, good. I was hoping it was something like that. But I just lost it. Which things?
Y then times y minus 1.
Thank you. This is number 4. A mathematician can't count. All right, you guys, I have to be somewhat selective because, again, I don't want to waste too much time blundering with my horrible arithmetic. I think clearly if y prime is equal to 0, my solutions are nice. I think I get two solutions, namely y equals 0 and y equals 1. I hope I'm not doing too many examples. I get the feeling I am doing too many examples. Humor me. Who cares? Make a full sentence in English.
At those two lines, the slope is 0 for the particular solution in general.
Nice. For any solution passing those two horizontal lines in green, my tangent line is going to be equal to 0 in terms of its slope. Are these equilibrium solutions?
Yes.
Yes.
Yes. And so I think both these horizontal lines happen to be solutions to the DE. Do you think any other solutions can pass through these horizontal lines? Do you think any other solutions can also pass through these horizontal lines somewhere?
Yes.
No.
Because the partial, I'm sorry, no, because the partial derivative of that with respect to y is continuous.
Very nice. Checking the existence uniqueness theorem. Here's my f. Clearly it's continuous everywhere. But if you look at the partial of f with respect to y, that 2 is just a linear expression of y, clearly continuous for all values of y, and of course x. Therefore, I think with these equilibrium solutions, these two horizontal line solutions, no other solutions pass through those horizontal lines except for themselves. So, trying to sketch those two solutions. X-axis, y-axis. However, if y prime is equal to, I don't know, you guys pick a nice number. I said, I don't know, you guys pick a nice number.
1, 2.
I can't hear you. Y equals it's 2. Yes, it's 2. I agree. Do you guys agree?
Yeah.
Okay, too many blank looks again. It's 2. Here's a y squared minus y. Subtract 2 from both sides. Y squared minus y minus 2 factors nicely into y minus 2 times y plus 1. But if y minus 2 is a factor to set equal to 0, then y equals positive solution, etc., etc. Let's do a little math. Okay, I guess that means in green, when I look at the lines y equals 2 and y equals negative 1, these are isoclines for which
The slope is negative.
the tangent lines have a slope of positive 2. How am I doing so far? Yes.
Is it only an equilibrium solution if it's both a y equals constant solution and zero at that particular point? So,
Sir, I just lost it. It's not your fault, it's mine. Can you repeat that?
is it only an equilibrium solution if your slope at that particular point is zero and it's y equals some constant solution?
Yes, but I think what you're saying is redundant.